Hello, everybody. In this video, we're going to be going over question 2, binary search tree insertion and removal. Before watching this video, I strongly recommend checking out the background video on binary search trees. Otherwise, parts of this video might not make entire sense. But anyways, let's get right into it. So the text of this question is, suppose that we have this following binary search tree. As you can see, we have a binary search tree here. And then we want to draw the final tree after we perform the following operations. And we have 6 operations here. Seeing as the first 4 operations are all insert operations, let's take some time to go over what insert in a binary search tree does. All right. Insertion is usually called using insert X. So we start at the, and this is a recursive function, all right? So we're gonna start at the parent node. And if the number at the parent node is equal to X, then insertion fails. So in other words, a binary search tree cannot have non-unique values. Every single value must be unique. And that also makes sense, right? Based on our understanding of how binary sort works. If the number at the parent node is less than X, however, we're going to travel down the left subtree and repeat this process. If the number at the parent node is greater than X, we're going to travel down the right subtree and repeat this process. However, if the subtree does not exist, we're going to insert X into the subtree that we would want to travel down to. So for example, if we look at this very basic binary search tree we constructed here with A, B, and C, if we want to insert X, well, if X is equal to A, then we're just gonna immediately terminate the program because we can't have duplicates, right? If X is less than A, we're gonna try to travel down into this left subtree here, into the subtree B. And if X, for example, is less than B again, we're gonna try to travel down into the left subtree of B, but we're gonna see that there is no left subtree, and then we're just gonna insert X into a new node right here, right? And so now let's take a look at these questions, right? Starting off with insert 2. So let's walk through this together, right? We're going to start at the parent node, which is 6. We're going to check to see if 2 equals 6. It does not. 2 is, in fact, less than 6. So we're going to travel into the left subtree. Now we're at 3. And we're going to repeat this process, right? Is 2 equal to 3? No, it isn't. 2 is less than 3. So we're going to travel to the left. And now 2 equals 2. And so because 2 already exists in a binary search tree, insertion fails. And so the answer is simply this program does nothing, right? Nothing has changed. All right, onto this question, insert 11. So once again, we're going to start at the parent node 6. 11 does not equal 6. 11 is not less than 6. 11 is greater than 6. So we're going to travel into the right subtree. Then 11 does not equal 10. 11 is not less than 10. 11 is greater than 10. So we're going to try to travel into the right subtree. But notice, because this 10 node does not have a right subtree, we're going to go into this last case, right? If the subtree does not exist, we insert X in as a subtree. And so we're going to draw a node right here, 11, and insert that into our tree, basically. And so as you can see here, yes, we have drawn an 11 as the right subtree of 10. All right, one last example before I give you one to do by yourselves. We're going to do insert 8, right? So once again, start at the parent node. 8 is greater than 6, we're going to travel right. 8 is less than 10, we're going to travel left. 8 is greater than 7, so we're going to travel right. And then 8 is less than 9, so we're going to try to travel left. But there is no left subtree, and so therefore we're going to insert X in to the left of 9, as you can see here. All right, and so now take a moment, pause this video, and try to solve insert 4 on your own. All right, once again, the walkthrough, we're going to start at 6. 4 is less than 6, going to go left. 4 is greater than 3, going to go right. 4 is less than 5, we're going to go left. That's where we insert 4 right there. All right, and so the next 2 questions are all about remove. So now let's take some time to break down how remove works, right? Remove has 3 main cases. Now, the first case is quite simple, right? The first case is where the node X that we want to remove has 0 subtrees, in which case that's pretty straightforward, right? So in this example tree we've constructed here, if we want to remove B, well, we can just, because B has no subtrees, we can just remove B simply and then proceed with Z of A. This is pretty intuitive in my opinion, right? There's a second case where X has 1 subtree, in which case you can simply remove X and promote its subtree. So if we're trying to remove A here, well then you'd basically cross out A and then we'd promote its subtree B to whichever subtree A was of Z. And so, the only change is that, right? We've basically connected this dot from Z to this dot B, skipping over A, right? Let's take a look at an example of this with remove 2 from this tree, right? When we are in the case, if we look at this tree, right, 2 has 1 subtree. And so we are in this case where X is 1 subtree, in which case we're going to simply remove 2, and we're going to draw this line from 3 that is currently connected to 2, to the subtree of 2, which is 1, like so. And then, as you can see, the answer is we just cut 2 out. We're going to connect 1 to 3. The last case of removal is a bit more complicated, and we're going to use a process that we call hybrid deletion. All right, and so this case is when the node that we want to remove has exactly 2 subtrees, and there are 2 variations to hybrid deletion. There is right hybrid deletion and left hybrid deletion. Starting with right hybrid deletion, we're going to go to the right subtree of whatever node we're trying to delete and find the smallest node inside of that subtree. Now, how can we go about finding the smallest node? Well, because of the unique construction of a binary search tree, the smallest node of any given tree is always guaranteed to be the leftmost node. And so we can recursively travel left in our subtree until we hit a node that has no left value, and therefore we know that node must contain the smallest value. Once we have found the smallest value, we're going to go back to our original node, the node that we're trying to delete. We're going to replace the value in that node with the value of the smallest value that we just found. Then we're going to remove the node with the smallest value. We're going to delete that node. And so in an example here, right, if we have this tree A, B, Z, and C, if we're going to do right hybrid deletion on A, well, we're going to first travel into the right subtree of A. So this is ZC right here. Then we're going to try to find the smallest value in this right subtree. So we're going to go left from Z into C. We're going to try to go left again and realize there is no other left value. And so C is the leftmost value, therefore C must be the smallest value in the right subtree. Then we're going to replace A with C, as you can see here, and then we're going to delete C. Right. The other variation is left hybrid deletion, and it's basically the same thing, except instead of going into the right subtree, we're going to instead go into the left subtree, and instead of finding the smallest node, we're going to find the largest node. And the largest node is the rightmost value. And so it's basically just the right subtree, but flipped. So take a moment actually as an exercise to convince yourself why these basically do the exact same thing. All right, now let's go ahead and apply this to our question, right? We're going to try to remove 6. And as you can see here, 6 has, it has 2 subtrees, right? So we're in the case where we want to use hybrid deletion. Now, there are two answers to this question, right? Because we can either use left hybrid deletion or we can use right hybrid deletion. On a test, it will either specify it or it's not going to mark you down on which one you use, right? So let's go ahead and try to do left hybrid deletion first, right? So we're going to move into the left subtree here. Then we're going to try to find the largest value inside of here. So we're going to go right until we cannot go right anymore. We're going to go right to 5. Then we're going to try to go right again and realize there is no more right value. So 5 is the rightmost value, and therefore 5 is the largest value in this left subtree. Then we're going to replace 6 with 5. We're going to write 5 in this box essentially, and then we're going to delete 5. And so when we say delete 5, we're reusing the remove function that we defined earlier, right? And as you'll notice, this is in the case, again, this is in the case where you have 1 subtree. And so therefore, when we delete 5, we're basically saying we're promoting 4 to where 5 was before. So if we go to the answer, right, 6 has become 5, which was the largest value in the left subtree. And then we have done remove 5 in the case where we had 1 subtree, like we learned before. All right, and now go ahead and take a moment to challenge yourself. Try to do right hybrid deletion on this program now. All right, now that you've thought about it for yourself, we're going to first go into the right subtree. We're going to go left to 7. We're going to try to go left again and realize there's nothing. So we're going to replace 6 with 7, then delete 7. 7 has 1 subtree, so we're going to promote 9 to the place where 7 used to be. And so our answer is this, right? The 7 and 6 have been swapped, and then we've deleted 7 and we've promoted 9. All right, now as a recap of question 2. So these are 2 basically fundamental functions that we need to know for binary search trees. First is insert. We're going to start the parent node and repeat this process recursively, right? If the number at the node we are currently at is equal to x, then it fails. Remember, binary search trees can only contain unique values. Then, if the number at the current node is less than x, we're going to travel down the left subtree and try to insert again. If the number at the current node is greater than x, we travel to the right subtree and repeat. And if this subtree does not exist, then we're going to insert x in as the left or right subtree, depending on which direction we try to travel in. The other important function is remove. So there are 3 cases. X has either 0, 1, or 2 subtrees. If there are 0 subtrees, it's pretty intuitive because we can delete x without changing anything else, right? So deleting x is easy. If we have one subtree, we're going to delete X and we're going to connect this one subtree to its parent node where X used to belong. And finally, with two subtrees, we use hybrid deletion, where in the right hybrid deletion, we go to the right subtree and find the smallest node, and then we repeat the process that we just learned. Right?